Alright, welcome back folks. So today we're going to be deriving n-dimensional spheres as well as the volume associated with those spheres. And along the way, one of my main objectives is to ensure that you feel like you have gotten a comprehensive approach and a complete picture for how this logic progresses, starting from some of the most generalized sort of statements about spheres. And that is so that you don't leave feeling dissatisfied by just a plethora of assumptions that are made along the way. That is, at least in my experience, one of the more frustrating things that I have seen or watched about the derivations of n-dimensional spheres. There's always tons of different equations or different formalities that are sort of arbitrarily chosen, and the viewer is supposed to take it at face value and assume that this is true and take the writer or the presenter's word for it. And that's fine. I mean, in the interest of time, that is of course perfectly valid. But for this in particular, I wanted to give you a complete picture. So with that in mind, this video is going to be a little bit longer. So strap in, get hyped. Let's derive some hyperspheres. Okay, so here we have ourselves a line. And not just any line. This line, of course, is a sphere, which I guess maybe is not nearly as obvious as I made it sound there. But with that in mind, if I generalize it as a sphere, it actually follows a very cohesive logic. Now, you have two intervals, which act as boundary points, constraining it, and then you have this middle interval that just slices it right down the middle, right? Well, what you're doing is essentially creating a radius. And what you're dividing is its diameter, which of course is half. Radius is of course half the diameter of any sphere. So if we describe it in such a way, we can simply call this a zero-dimensional sphere in one-dimensional Euclidean space, or a ball. So we're going to write it like so. So we have a ball in one-dimensional Euclidean space as a function of r. Okay? So moving down here, we have ourselves a circle, which is essentially just moving up a dimension. Now, we can obviously describe this in terms of its radius, and this is probably very familiar to many of you, but you might not expect it to be labeled as a sphere. But once again, showing it through this logic, it actually makes a lot of sense. So this would effectively be a one-dimensional sphere in two-dimensional Euclidean space. So we have ball 2. So ball in two-dimensional Euclidean space as a function of r, right? Now over here, we have ourselves a sphere. Now obviously this is on a two-dimensional plane, but you can see that it is clearly representing a sphere. Now, with that in mind, topologically speaking, this is a two-dimensional sphere in three-dimensional Euclidean space. So it's following the same sort of logical progression. So we're going to call this V3 as a function of r. Now we can describe their volumes fairly simply. Now this, as stated before, is simply just a line constraining 2 points, which acts as the boundary separating, or the boundary creating the diameter of that interval, where when you split it down the middle, it creates a radius. So we can actually call this V1 as a function of r. So for the volume, it would just be 2 times r, right? Okay, so we have our circle now, which we can describe similarly to what we described in our first case. So V2 now, as a function of r, is just going to be the familiar equation, which is generally associated with the area of a circle, but based upon the generalizations that we're making, this is the volume of a ball in two-dimensional Euclidean space, which is in fact its area. But we're calling it volume, so we can ensure that we follow a logical progression here. So pi r squared, right? is our volume. So for this is, of course, just V3 is a function of r. So for our ball in three-dimensional Euclidean space, that is going to be equal to 4/3 pi r cubed, right? So now what I want to first do is derive the equation here for the volume of a sphere, right? That is where I want to start, and then we can actually start progressing from there. So we have ourselves a circle on a Cartesian coordinate plane. Now we can actually use a two-dimensional plane to derive the volume of a sphere, and just requires some neat little mathematics. Now we're going to have to use some integration, of course, but first we want to generalize the cross-sectional area of this sphere that we're going to be drawing. So we kind of have a cross-section right here, right? Just split right down the middle. Oops, try that again. So we have our cross-section at the point at which the area of the little sliver is the largest. But we want to integrate from both boundary points. So both boundary points being labeled as r and negative r. And then on the y-plane, r and negative r. And this is, of course, y and x. So now let's draw another little cross-section that shrinks down towards that positive boundary point r. So we're going to have ourselves a little cross-section of that sphere. And now what we want to do is draw a line from the origin that extends all the way up to the surface. And at the sort of top of that smaller cross-section. And we can draw ourselves a line here, which goes from there to there. So, now, what we want to do is, solve for the smaller radius, because as you can see here, along the horizontal axis, where this leg of the triangle that we have drawn extends from the axis to the boundary, well, that is simply just the radius. So we need to, that is what our objective is. That is what we are trying to figure out. So this right here is just r, little r. We'll call it little r, okay? Now, the point along the horizontal axis that we want to sort of label as our other leg for this right triangle is just going to be x, right? So this right here is just x, of course. And the hypotenuse of this triangle is just r. Now, we can actually make ourselves our equation using good old Pythagoras, right? So we're going to have r squared is equal to, what do we have here? So we're going to have r squared plus x squared. And remember, we are trying to solve for little r. That is what we want, because this will set up our boundary conditions to where we need to be, and then we can integrate over all the cross sections along the sphere. So solving for r, or little r, will give us, so r equals, and then obviously taking the square root will give us equal to, have our square root of r squared minus x squared, right? Now, we can actually set up our integral now that we have this. So let's do that. So our volume, our three-dimensional volume as a function of r is going to be equal to the integral of our volume, our v sub 2, essentially. So we're going to have our integral from negative r to r of v2 as a function of r, and then we are going to be differentiating with respect to x. Or our limit of integration is going to be with respect to x. So now what we can do is, what we've already proved or shown is that v sub 2 is just pi r squared. So what we want is to substitute our r in for the r in our two-dimensional sphere in our one-dimensional sphere in two-dimensional Euclidean space. So that is what we're going to be substituting. So we have v3 as a function of r equal to, well, we can actually pull pi out right away. So we're going to have pi, and then we're going to integrate from negative r to r. And then we are going to have r squared that we're substituting this r in for. And the square root is going to go away, so we'll cancel that out. So then we will have, let me see here. So we're going to have r squared minus x squared, parentheses, with respect to x. Alright, so now we can start integrating. So let's do that. So first, what we're going to have is pi, we're going to have pi out here, and then we can actually get rid of that. So we can take the indefinite integral. We have negative r and r, and then that's going to give us r squared, and then we're going to have x here minus x cubed over 3. Okay, so now what we can do is just take the difference between the limits, which we will do now. So pi, obviously remaining on the outside, we're going to have r cubed, that is not an r cubed minus r cubed over 3. And then minus negative r cubed minus r cubed over 3. Okay, so now what we can do is, of course, just sort of simplify this out, and this one right here is going to be 2r cubed over 3, and that is going to be subtracted from negative, so this one is going to be negative 2r cubed over 3. And then of course we add them, and lo and behold we have the volume of the sphere. So we're going to have 4/3 pi r cubed. Okay, so now we've gotten that out of the way, let's start moving on and use some similar techniques from what I've used in previous videos. So now what we're going to use is our Gaussian integral, and it might not seem obvious that this has any relationship between spheres at all, but it is in fact very, very closely related to any sort of spherical symmetry that you might encounter. And that should be apparent based upon my last video, which, if you would like to see me solve the Gaussian integral in polar coordinates, there is a link in the description, and you can see a more comprehensive approach. So with that in mind, I'm just going to set up and sort of breeze through this, and like I said, if you want to see a more complete sort of video, just check out the link. So we're going to have our Gaussian integral, where we're just going to call that g, of course, and if we square this, so we square g, we can write it like so. So we're going to have two integrals now. We're going to have a double one, negative infinity to infinity, of e raised to the negative, so we're going to call this x subscript 1 squared plus x subscript 2 squared. So dx1 and then dx2. Okay, so at this point we can naturally convert it to polar coordinates. So let's do that. We're going to obviously have our 0 to 2 pi on the outside here, and this is going to go from 0 to infinity, and we're going to have e to the negative r squared times r for our Jacobian, and dr, and then we are going to do d omega subscript 1, which is a little different than last time, but you'll see d omega 1 is just equal to d theta. It might not seem like that's necessary for this purpose, but it'll sort of make sense later on here. So first, what we do know is that this whole thing is just equal to pi, as we've proved in my last video. Like I said, if you want to check it out, check out the link. So this obviously is, of course, g squared equal to pi. And if we take the square root, then we're just left with g is equal to the square root of pi. Oops. Alright, so now we want to move this up a dimension. So now what we are going to do is solve this integral in spherical coordinates. So moving from polar, the only natural course to take is to enter the spherical realm. And to do that, let's obviously take our integral from negative infinity to infinity of e to the negative x squared dx. And we are going to cube it. Okay? So by doing that, we just simply get our integrals from negative infinity to infinity. And I'm just going to leave out the other limits, just in the interest of time. So we're going to have e raised to the negative x squared 1 plus x2 squared plus x3 squared dx1, dx2, and dx3. Now, to describe this in terms of spherical coordinates, and we can sort of represent this using the physics notation. Sorry, I can't I can't write and talk at the same time, apparently. So, in spherical coordinates, we have our radial direction, where we have r, and then our polar angle, which is theta, and then our correct me if I'm pronouncing this wrong, our azimuthal angle, which is just our horizontal rotation. So we have radial, polar, and azimuthal. Okay, so with that in mind, we can take our limits of integration and convert them. So to do that, let's kind of zoom in here. We're going to have dx1, dx2, dx3, and that is going to be equal to r squared. Now, some people use rho instead of r, but I'm trying to make sure there's consistency here, so there's no confusion. So r squared times sine of theta times dr times d theta times d phi. Okay, so now this right here, oops, let's take these and we're going to call it d omega 2. Right? So this is going to be r squared times dr times d omega 2. Okay? That's how we're gonna write it, because this sort of gives you a little bit of key intuition into how we're going to be generalizing our n-dimensional spheres and the integrals that we're going to be needing. So, with that in mind, what we need is our integral, where we have this going from 0 to 2 pi, because that is the domain of our azimuthal angle, and our polar angle is going to go from 0 to pi. And then, of course, our radial angle is from 0 to infinity. And we have here ourselves e raised to the negative r squared times r squared, and then d r d omega, subscript 2. Alrighty, so first, let's sort of put this aside here and solve for the integrals on the outer ends here. So what we're going to have just right here, from 0 to infinity, e raised to the negative r squared times r squared, and over here we have our integral from 0 to 2 pi, and the inner from 0 to pi, and what we're going to have is sine of theta, as we expressed over there. So sine of theta, and then we are going to have d theta, d phi. Okay, so taking the indefinite interval of sine of theta is just going to be negative cosine, so this is nothing but our interval from 0 to 2 pi, and obviously from 0 to pi, after taking the indefinite interval, we're going to have negative cosine of theta, and then close that off, and then d phi again. Well, taking the difference between the limits of negative cosine here, we are going to end up with 2. So this is just going to be 2. And if we just integrate now from 0 to 2 pi of 2 d phi, well, that is just going to give us 4 pi. Great. So now we can take that 4 pi and place that on the outside of our integral of this term right here. So 4 pi. Right? Alright, so now we can label this entire integral here, along with its constant value that we have extracted, as I. So I is equal to all of this. Now, the integral itself, we can actually just call j. And that is what we're going to be working off of from here on. Now I did make a video previously about the Leibniz rule for integration, or the Feynman. So we are going to be using that here to solve for this integral. And I just realized I forgot my limit. So dr. Don't forget those. So first, what we want to examine is the second derivative of this term right here. So let's do that. So we're going to have second derivative squared with respect to r of e raised to the negative r squared. Well, that is simply just equal to the derivative of this now with respect to r is just negative 2r e raised to the negative r squared. And if we take the derivative again and use the product rule, then we have just 4r squared e raised to the negative r squared minus 2e raised to the negative r squared. Okay, so keeping that in mind, we can obviously take the improper integral of this term right here. So if we actually put the derivative within the integral based upon the Leibniz rule of integration, we can actually extract it. So what we're going to have is from 0 to infinity of d squared dr squared of e raised to the negative r squared dr. Well, this, as I've just stated, we can actually pull out the differential because it is no longer dependent on r. And what this ends up giving us is d squared over dr squared of our integral from 0 to infinity times e raised to the negative r squared dr. Well, if you evaluate this integral, you just get a constant. And if you take the second derivative of a constant, you get 0. So that is just 0. So we can now just set what we just solved for, our differential. So 4r squared e raised to the negative r squared minus 2e to the negative r squared equals 0, right? Because that is what we have just proved. So with that in mind, we can move this over to the other side. And then I'm going to divide by 4. And what we're going to have is now the improper integral of both sides. We have to include that because that's what we did to this side. So we need to ensure that we maintain that consistency. So we're going to have our integral from 0 to infinity of r squared e raised to the negative r squared equals 1/2, because obviously 2 divided by 4, that's going to be 1/2. And then we're going to have our integral from 0 to infinity of e to the negative r squared dr. I forgot dr over here. Okay, so what is this? We have just defined this previously as j. So if that's j, then what we have is j is equal to 1/2 of the integral 0 to infinity of e raised to the negative r squared dr. Now, what we can do is adjust the boundary limits of this integral with a neat little trick. So what this essentially means is if we were to draw this on a graph where we have this bell-shaped curve which describes our Gaussian integral, it's not symmetric, but bear with me, well then we have one side that goes on to infinity, to plus infinity. So from 0 to infinity, right? Which is just 1/2 of 0, or our integral from 0 to infinity of e to the negative r squared dr. Now we can draw the same on the other side, which is the same thing. So 1/2, except the difference is it's going from that to negative infinity, right? So 1/2 now with essentially different limits. So this is going to go from 0 to negative infinity of e to the negative r squared dr. Now if we combine these, we are simply just dividing them by 2. And to do that, we will have now j is equal to 1/4. Since we're dividing by 2, we can change these boundary limits from negative infinity to infinity of e to the negative r squared. Well, what is this? This is just our Gaussian integral, which is essentially the whole purpose of changing these boundary limits so that we can actually solve something we know how to solve. And what we want to do first is square this whole equation, change our r variable from its original dummy variable form to some other arbitrary selection, x we'll call it, and then x subscript 1 and 2. So if we square j, then we're left with 1/4 times our interval from negative infinity to infinity of, keep forgetting my limits, so e raised to the negative r, I just said I'm changing that, so we're going to call it x squared, so x1, subscript 1, with respect to x1, times 1/4 of negative infinity to infinity, and then we're going to have e raised to the negative x2 squared dx2. Okay, so if we just combine these, well, we have nothing but, let's change that, our j squared, that is equal to 1/16, with our integrals from negative infinity to infinity, of e raised to the negative x squared 1 plus x2 squared with respect to x1 and dx2. Ooh, alright, so with that in mind, now we can actually convert this to polar. So we're going from spherical to polar, and there's just a lot of circular logic in this episode. So with that in mind, now we can convert this to our integral that goes from 0 to 2 pi, and of course we have 1/16 out here, and our inner integral from 0 to infinity of e to the negative r squared, again back to r, and our Jacobian r, just with our limits of integration as dr d theta. Now we know what this answer is. We've just proven it. And this right here is just pi. However, we know that that's not the answer because j squared is equal to pi/16. And if we take the square root, then we get j is equal to the square root of pi/4. And of course that is not the answer, because if you recall, I is equal to 4 pi times j. And we need to plug j in for that. So I is equal to 4 pi times the square root of pi/4. These will cancel, and I is just equal to pi raised to 3/2, which is to the 3/2, right? And that is the Gaussian integral solved in spherical coordinates and polar coordinates. So now we can actually finally start working on the equation for n dimensions. Now, to do that, what we need, let's segment this off here, what we need is our Gaussian integral yet again. So, but this time we're going to generalize it for n dimensions, for n terms, right? We're going to have our integral from negative infinity to infinity of e raised to the negative x squared dx. And we're going to raise this to the nth power as opposed to 3, 4. We're going to generalize it for n. Now, what does that give us? Well, we're just going to have our integral that goes from negative infinity to infinity, and our integral from negative infinity to infinity of e raised to the negative, parentheses, x 1 squared plus dot 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 plus x sub n squared, because we're going n terms here. So dxn. Okay, so this is what we're going to be working off of. But first, let's sort of invoke that variable that we have been using that hasn't really been expounded upon at this point. So before we were labeling our outer limits d omega and d omega 1, d omega 2. Well, let's take a look at what that is. So d omega 1 right here is what we solved for the first time for our first Gaussian integral. Now, what is that? Well, that's obviously the integral from 0 to 2 pi, right? And that is, of course, just the integral 0 to 2 pi of d theta. Now, if we look at this little diagram here, well, what do we got? So we have a circle that we're going to be integrating over, or that we had already integrated over, and it is moving along the surface, or the circumference of this circle for d theta. And we are just kind of slicing little bits, and slicing more and more and more and more until we cover the entire circle, and which is obviously, of course, 2 pi radians. So that is, of course, the outer edge of our circle. So this is representing the surface of our circle, which is what we have described before. It is our one-dimensional ball in two-dimensional Euclidean space. Now, with this in mind, for d omega 3 from 0 to 2 pi, and then our integral from 0 to pi of d omega 2, well, this was, of course, just, actually, let me write that here. So d omega 2 is just sine of theta with respect to d theta d phi. So this right here is all d omega 2. Well, what is that? And what we are describing with this double integral, when we integrate over our polar and azimuthal angle, we are simply just describing the surface area of a two-sphere in three-dimensional Euclidean space. And what we're integrating over is the surface area. So we are taking little infinitesimal chunks, little slices that span across the totality of this surface, which is essentially just our surface area. So what these terms here are representing are nothing but S being surface area, subscript n minus 1, because you need to relegate back to a lower dimension, at least one more dimension, to describe the surface area of whatever sphere you are associating with that surface area. So S sub n minus 1 is equal to our new d omega term, n minus 1. Okay, so having described that, we can now create ourselves a more general equation. So what we now have here is just our integral from 0 to infinity of e raised to the negative r squared times r to the n minus 1 dr. And then over here, we just have the surface area portion of our n-dimensional sphere, or just our integral, of course. So from some value to some arbitrary value. I'm just leaving it at that for now. So d omega n minus 1 here, right? That is where we're going to leave it. But first, we want to sort of set our sights on this integral here. So as stated before, we want to put our raised to the n minus 1 in terms of r squared. So, and then we also want to sort of extract an r from this. So you'll see why that becomes necessary in a moment. So what we're going to do is put our integral from 0 to infinity of e raised to the negative r squared of r to the n minus 2 times 1/2 times 2r dr here. Because obviously this 1/2 might seem just a little bit unnecessary, but it becomes very useful in a moment here. But obviously if you were to multiply those two r's together, you would get n minus 1. Very simple stuff. So now what we want to do is put r in terms of r squared. So that means, off to the side here, we're going to have a little note, r squared raised to the 1/2 times n minus 1. Well, that is simply just going to give us what we started with. So obviously if we multiply that over, we're just going to have n minus 2. So r raised to the n minus 2. So these are the same thing. Now, with that in mind, we can actually rewrite this. So integral from 0 to infinity of e raised to the negative r squared times r squared raised to the 1/2 n minus 1 times 1/2 times 2r dr. Okay, so what we can do with that is finally use some U-Substitution, right? So u, we'll say, is equal to r squared, and differentiating that, du with respect to r is going to be 2r dr. And now we can actually just plug in what we need. So what that gives us is our integral from 0 to infinity, and we're going to have e raised to the negative u times u raised to the n over 2 minus 1, and then that 1/2 is still there, but we obviously substitute du in for 2r dr. So du, and that 1/2 I'm just going to put right on the outside of this integral here. So now, this might not seem like much, but this happens to be a very interesting equation. This is what's known as the gamma function, just with a different sort of independent variable. So what the gamma function is, if you recall, is gamma as a function of n is equal to the improper integral from 0 to infinity of e raised to the negative x times x to the n minus 1 dx. This is a key component into developing our formalism that we need for n-dimensional spheres and the hypervolume associated. So we can use that, but all we really need to change is the n value here. So this is just going to be 1/2 gamma of n over 2 is equal to 1/2 times the integral from 0 to infinity of e raised to the negative u of u raised to the n over 2 minus 1 with respect to du. So now, using that, we know that the gamma has some very interesting properties. And this is where there are some minor assumptions that you'll just kind of have to take my word for, unfortunately, because that would just really derail us entirely if I started going into the different properties associated with the gamma function, because they are vast. And what you basically essentially just need to know about the gamma function is that it is an extension of the factorial numbers, and there's also another key property, which is, so gamma properties. So gamma properties, that tells you the gamma of n plus 1 is equal to n times gamma of n. And the other one that we're going to need is, since it is the extension of the factorials, well, gamma of n is also just equal to n minus 1 factorial. So these are very important properties that we're going to be using along the way. So now that we've sort of generalized and created a function associated with our n-dimensional Gaussian, as you might call it, well, remember, we have left out a key component, the surface area. And what was the surface area? Well, that was just s sub n minus 1. Well, now that we know that 1/2 of our gamma function times, as a function of n over 2, well, we need to, of course, multiply it by what we have already sort of described and generalized. So that is going to be s of n minus 1 is equal to, well, what would it be equal to? Well, what did we describe for our n-dimensional integral to begin with? Well, we just raised our Gaussian integral to the nth power. Well, this is, of course, equal to negative infinity to infinity of e raised to the negative x squared dx, and then parentheses raised to the nth power. Well, what is this? Well, this, if we follow the approach that we have already described, this integral always seems to be some square root multiple of the next one as you increase dimensions. So that would essentially mean that the answer of this integral is just pi raised to the n over 2. Now we can actually write 1/2 of our gamma as a function of n over 2 times s sub n minus 1. That is going to be equal to pi raised to the n over 2. And what we want to solve for is our surface area, because we don't really know how to integrate over that, because we don't know what variables or what quantities are going to be needed along the way. That's why this gamma function is very, very important. So this is going to be s sub n minus 1. That is going to be equal to pi raised to the n over 2 power over 1/2 times gamma of n over 2. Alrighty, so now keep in mind, this is the surface area of our n-dimensional sphere, right? We need volume. That's what we're going for. Well, that's pretty simple. All we need at that point is our volume of n sub n as a function of r is going to be equal to just our surface area, n minus 1 sub n minus 1, times our radius raised to the nth power. So keeping that in mind, we will be using that. But first, we are going to solve for our n values, starting with n equals 1. So n equals 1. Well, let's see what that gives us. So we're going to have s sub n minus 1. Well, that's just going to be s sub 0. And that is what we've described before. That is what it should be, at least, if this is all correct. It should be our zero-dimensional sphere in one-dimensional Euclidean space. So we're going to have our s sub 0 equal to, well, this is going to be pi raised to the 1/2, because n is 1 now, over 1/2 times gamma of 1/2. Okay, so now what we want to do is solve for gamma as a function of 1/2. And to do that, we can actually just over to the side here, we can have our integral from 0 to infinity of e raised to the negative x. And remember, gamma is 1/2, so therefore our x value is going to be 1/2 minus 1, which is negative 1/2. Negative 1/2 dx. So, how do we solve this? Well, this is a little bit of a different sort of substitution than you might be used to, but this is probably the hardest solution thus far. N equals 1 is probably the more complicated solution. There's a lot of different ways of solving it, but this one I think is probably my personal favorite. So what we want to do is set x equal to t squared, right? Now we're going to differentiate x with respect to t. So that's going to give us dx is equal to 2t dt. Now, if we were to plug this in, we're going to have an integral from 0 to infinity of e raised to the negative t squared. And recall that we have this 1/2 as well, so don't forget that. We are going to be using that. So we are going to have this x value becoming t, but however, x is t squared. So if we brought that down to the denominator, then we have 1 over t squared raised to the 1/2, which is just t. So that is going to be times 1 over t. And then 2 dt. So filling in for dx. So we're going to have 2 t dt. And we can cancel out these t variables and pull out this 2. And we have this from 0 to infinity of e to the negative t squared dt. Well, this looks almost like our Gaussian integral, but once again, we need to adjust our boundary limits. Since we are multiplying this function by 2, then we are just going to have our Gaussian integral from negative infinity to infinity of e raised to the negative t squared dt. Okay, so this, we know, is just the square root of pi. So now we can actually plug this in for our gamma function over here. And let's do that. So our surface area for n equals 1 is going to be equal to the square root of pi over 1/2 times the square root of pi. Well, what's going to happen here? Well, we're going to cancel out our square root of pi values, and we're just left with 2. But of course, if we want the volume, we need to multiply by r to the nth power. So that means our volume, or v sub 1, as a function of r, is going to be equal to 2 times r raised to the nth power, but n equals 1, so r is 1. So there we go. That is consistent with what we described at the beginning of this video. That is great. So let's try n equals 2. So for n equals 2, we can actually just fill in our surface area, which is 2 minus 1. So 2 minus 1 is 1. So s sub n of 1, or s sub 1, excuse me, that is going to be equal to just pi, because n over 2, as we know our equation to be, is just going to be 1. So pi divided by our gamma of 1/2 of our gamma as a function of, well, 2 over 2 is just 1. So that's going to be 1. But there's a better way to come at this, because we know that gamma, as we pointed out before, of n plus 1, well, that is of course just equal to n times gamma of n. Well, we can actually describe the original formalism using that. So we know that 1/2 of gamma of n over 2, that must also be equal to gamma of n over 2 plus 1, right? If we were going to maintain this logic here. So we can rewrite that. So therefore, our s sub 1 is going to be equal to pi divided by gamma of, well, n over 2, n equals 2, so we're going to have 1 plus 1, which equals 2. So gamma of 2, that is going to be equal to, well, let's pull out another property from the gamma grab bag. We're going to have our pi divided by, well, this, of course, gamma of 2, is also equal to 2 minus 1 factorial, which is just 1 factorial. Therefore, gamma as a function of 2 is equal to 1. So pi divided by 1 is just going to be pi. But remember, we want volume. So the volume sub 2, the function of r, that is going to be equal to pi r to the nth power, n is 2, r squared. Great. Also consistent. Now, let's move on to v sub 3. Or n equals 3, that is. So n equals 3. Well, how shall we describe that? Well, we're going to have s sub n minus 1. 3 minus 1 is 2, so s sub 2, which equals, well, what do we have here? We're going to have pi, of course, raised to the n over 2 power. Well, n equals 3, so we're going to have 3 over 2. Divided by, well, let's see, what do we have here? We've just shown that gamma, 1/2 gamma of n over 2 is equal to n over 2 plus 1. So we can describe it that way. So let's try that. So we're going to have gamma with 3 over 2 plus 1. Okay? So now, what I propose that we do is actually rearrange our gamma function to look like this. So we're going to have pi raised to the 3 over 2 power. Well, let's pull out our 3 over 2 factor. So we're going to have 3 over 2, and then gamma as a function of 3 over 2, right? Well, it may not seem like it, but we've actually just solved for gamma of 3 over 2. So we don't have to go through the integral or all that messy work to solve it. So gamma of 3 over 2, where is that? So this right here, for what we solve for when n is equal to 1, well, 1/2 times gamma of 1/2 is the same as gamma of 1/2 plus 1. And that is equal to gamma of 3/2. So, with that in mind, we know that this has to be the square root of pi over 2. So we can actually just fill in this portion here with the square root of pi over 2, which we have now pi raised to the 3/2 divided by 3 over 2 times the square root of pi over 2. Multiplying these out, that is going to give us pi raised to the 3 over 2 divided by 3 over 4 times the square root of pi. Now, let's us sort of rearrange this, of course. This is going to give us 4/3 times, well, if we do our exponent rules, 3/2 minus 1/2, well, that's just 2/2, which is 1. So we're going to have 4/3 pi. And that looks familiar, doesn't it? So now we can just fill in our radius now, our radial portion. So v3 as a function of r is equal to 4/3 pi r cubed. Now, great. Now let's get into the more interesting part of this entire lesson here. So 4 dimensions. N equals 4. Let's see what that looks like. N is equal to 4. We're going to have S of 4 minus 1, which is 3, so S sub 3. Well, that's going to be equal to pi, and this is going to be 4 over 2, so that's just going to be 2. So this is going to be squared now. So pi squared, and what we have here is gamma of 4 over 2 plus 1, which is 2 plus 1, which is just gamma of 3. So we're going to have pi squared over gamma of 3, and therefore this is also equal to 3 minus 1 factorial. So 3 minus 1 factorial is just 2 factorial, which is just 2. So therefore, the volume of our 4-dimensional sphere, or our 3-sphere in 4-dimensional Euclidean space, is simply just v as a function of r equals 1/2 pi squared times r to the 4th power. And that is the volume for our 4-dimensional sphere. So what you're all seeing here now is our representation of n-dimensional spheres, starting with, of course, our non-hyperspheres. So forgive me if the title is a little bit misleading. However, what this is exemplifying is the fact that it is creating an increasing arc as you increase the dimensions. So for the radius equal to 1, the volume is increasing very rapidly. So it'll increase all the way up to v sub 5. And once it hits v sub 5, it decreases drastically, which is kind of a surprising result, if you ask me, because as you continuously increase dimensions, once you hit the threshold of 5, the value or the magnitude of these volumes decreases faster than any exponential value you can find. So I found this to be particularly interesting, and I hope you do too. So evidently it would seem that you have made it to the end of the video. Congratulations, and thank you for making it this far, if you did. And with that in mind, I hope you at least got something out of this video and have a much more fonder appreciation for mathematics and the abstractions that can be employed in order to find things that are beyond our realm of conception. We obviously can't perceive of a 4-dimensional sphere or anything beyond that, let alone understand what they look like. Now, obviously, with the tricky little mathematical tools that we've been able to use, that is of course possible to describe, which is pretty amazing in and of itself. So thanks again for watching. I really appreciate it. And if you would like to see more videos like this in the future, please subscribe and leave a comment if you have any further questions.